as all of you probably remember from yesterday when I tortured you with a high-level prezzo, today I'm going to torture you with a very bottom-up trip through the actual code that we're open sourcing through FD.io. The right way of saying it is it's going to be a little bit of a George Burns tour of the Louvre, which is to say Gracie Allen one time told George Burns, hey, take the kids to the Louvre, well, thinking that she was going to get 3 hours apiece. And what they ended up getting was, here's the Venus de Milo, here's the Mona Lisa, and there's the door. So this is going to go by pretty quickly. I apologize in advance. I've been working on this stuff long enough for it to be in high school if it was a kid. And I'm sort of Ebola patient number one. I was there on day one at the beginning of the outbreak. And as a result, I apologize. I'm probably not going to do the optimal job for everybody in the room. There are plenty of Cisco folks around there, the Dave squad, Dave Wallace, Dave Damian, and so on, who are here to help with detailed questions, with laptop setup questions. By way of a rough agenda, I'm going to go through the key directories, kind of a what's where sort of thing. I'm going to go through the startup sequence, which you might think is a lot of mind-numbing detail, but actually the idea is to give you some hooks to be able to navigate it yourself. One more silly joke. For people working reasonably hard on the source base, it's been empirically shown that it takes between a month and, irritatingly, the term of someone's natural life to get where they're really comfortable in the environment and working productively. So don't expect too much. We're going to post these recordings online, on the wiki once they've been cooked and have had some indices put aside, put on side, so you can find topics in them again. So it's not, you don't have to get everything. I want people to get the flavor and to get enough so that they can navigate the source base themselves and get where they're going. The other thing is, I'm a pretty hardcore Emacs guy. I don't know from your favorite text editor, but all this stuff is going to go by in Emacs. Necessarily, I have to sit down and, sit down because we're going to be at this for a while. So by way of navigation, if you guys on your laptops can run yourselves to basically, let's see, wherever you drop the thing down, presumably, JIT VPP at that level, one up from build root, where I'm sitting, you'll see a set of directories. Now, the cscope stuff is not of any particular import. Build data contains what amount to makefile fragments, which tell the VPP build system, how to build certain components. So might as well take a very quick look at one of them. Build data. Build data. Oh yeah, duh. Build data packages are the list of components that are run together to form the system. For example, VPP.mk is the final container app step. This is it ends up being a single pass build system where we use AutoConf automake natively across all the components. It's, is AutoConf automake the greatest solution since sliced bread to everything? No, but it turns out to work pretty well. What we end up doing is we say, okay, in order to build the VPP component, we need to have installed all these others. And we'll go into some details. Again, a little bit of a recursive descent. I don't want to go too deep here right now. So backing up to where we were a second ago. Oh, great. Build root is actually the root of the build system. It's where all of the executables and tools are built. The main makefile in build root is fairly complicated. My chief collaborator early on in this work, Elliot Dresselhaus, built an absolutely brilliant single-pass build system, largely data-driven, driven by sucking fragments into the running version of Gmake. There's certainly room for innovation here. We can imagine doing a number of different things to build the system. This one works pretty well. It has the advantage that the dependency processing is exactly accurate. The only time you really might be tempted to start over from scratch is if you pull a bunch of updates. It's frequently faster to just wipe out everything and start over. On the other hand, the build system really works. You're not going to see dependency issues, and it's Ccache enabled, which means after the first build of everything, single touch builds are real fast. Yep. Hey, Vincent, we need, definitely for you, we especially need a mic.
Sorry to interrupt you there, but just to get the background, the build system from the DPDK and from the VPP are completely different. I mean, should we try to merge them or to converge them?
At the moment, what we're doing is we use the DPDK, make files verbatim with just the least little bit of configuration. We don't really want to mess with DPDK. Converging them at some point is possible. I will point out that both build systems are at a certain level of complexity. What we're doing with DPDK, we might as well get on that topic for a second, is if you look in the DPDK directory that we're open sourcing, it's a pull and very lightly patched scheme. It's not, we touch nothing there. We use the DPDK build-in for a verbatim, and there's no immediate plans to do anything except that. Make sense? Converging them, is certainly a discussion we can have. At any rate, back to. So we went over DPDK quickly. The sample plugin is exactly completely worked out way, sample of building a plugin. Typically, the way of doing plugin development is to install the engine development package and to configure and build the sample plugin based on installed header files, installed libraries right on the platform. That there's no need to rebuild the engine to build plugins at all. SVM, as you probably recall, the control plane binary APIs use shared virtual memory between the set of clients and the VPP engine itself, and SVM is the shared VM library. Test, Dave Wallace will talk about. VLib is the vector library. It's the means by which we do vector processing. I'm going to go through some of the init sequence, how the main dispatcher works in VLib, because without some knowledge of it and without having seen it, the node types won't make a lot of sense. So we'll go through there. VLib API is the set of API infrastructure routines layered on top of shared virtual memory, which actually allow clients to connect and to communicate with the overall process. VNet is the network stack. It's by far the largest piece. VPP is the container app that we're currently building. Now, folks are free to build their own container apps. What you'll see is that in most cases, the various libraries I was just yakking about are actually DLLs that are installed in the platform. VNet is actually a static library, figuring that you want to play selecting items from a menu. Not everybody's going to want MPLS. Not everybody's going to want SRP, PPP, you name it. And that's a level of customization you can do at compile time to say, here's what I want out of the networking stack. VPP API Gen, as we probably described, is the API compiler. It takes something that looks a lot like decorated C type defs and spits out real C type defs. VPP API test is the canonical binary API client. We'll play with that a little bit later. We'll tickle it a little bit later. VPP infra is the foundation libraries. It's things like dynamic arrays, vectors, bitmaps, hashes, hashes of various sorts. There's even a simulated annealing driver if anybody likes to play with optimization problems. Someone can correct my math there, but at any rate, there are a lot of goodies that we're not even necessarily using. VPP JAPI are the Java bindings, which Dave Wallace will talk some about a bit later. So again, with no further ado, let's go find the main routine, because it's the place where all the action starts, and it's in VPP VNet main.c. Whoops. VPP. Duh. Sorry, everybody. My brain hasn't been adequately caffeinated yet. And the first thing you'll see is, some nonsense of this form. This is the main init of the the library main init. Reason you're going to see library plugin reference there is that if you remember the linker map I just talked my way through a little bit, it turns out that one of the things you can imagine a plugin doing is to refer to some symbol in the static library that the container app isn't touching. We found and listed in a way such that all of the all of the interesting symbols are available to plugins. This library plugin reference just makes sure that the DLL that captures all of those linkable references is actually linked into the container app. Again, the linking architecture is a little complicated. Don't obsess about it, but that's what that one means. And here's the, effectively the selecting out of the menu that we do all over the place. The call init function guy, you'll see in a moment that there are init functions for subblocks, for individual graph nodes, for subsystems in the VPP engine. And this is a way of ensuring, first of all, that the container app actually links against them, and second of all, that they're actually called. Now, there are dependencies between init functions. What we end up doing is, if a certain init function depends on some other init functions, like the thing we're looking at here is the application main init guy, and what we'll end up doing is we'll say, oh yeah, well, I want to make sure that all of these other things are both present, accounted for, and have been called. What it ends up doing is it implicitly does a partial order resolution. You can obviously break the scheme, but it turns out it just basically works to say, oh, I need to be sure that the IP stack has been initialized. Okay, quick, call it, and then continue with what I'm doing. And effectively, you're doing partial order resolution there. So now, at the end of this guy, when we say, okay, here's an epic catalog of everything in the world that it's doing, you'll see this vlib init function macro. These macros are actually ubiquitous across the source base. What they're doing is actually kind of cute. It's one of the little engineering things. Again, this is kind of a bottom-up engineering, random walk through the universe. Meta X, cscope, fine, right. Right, so let's go find this guy. And if we get over here into the init function thing, I'm not going to bore you with all the details, but this is how the init functions actually work, is they're generating little tiny code snippets that turn out to be, have constructor attribute. What that means to the compiler and the linker is these guys will get fired up before main ever happens, which says, okay, go run this constructor function. What is it doing? If you stare cross-eyed at this for a second, you'll realize that it's making a singly linked list of all of the init functions. And son of a gun, if there isn't a piece of code that actually goes and runs them all. There are multiple flavors of these. There are config functions, there are early init functions, and so on that are used in various places. But the scheme is really simplicity itself. It's constructor function based. Why is that important? It's important because otherwise plugins become very second-class citizens. That what we've really achieved is that plugins can look exactly like mainline code. In fact, the process of picking a plugin up, throwing it into the engine, or picking some engine code up and throwing it into a plugin is, cut, paste, fiddle with the makefile, done. And it really, you really want it to be that way. The other thing is this scheme survives the kernel segment base address randomization scheme, minus PIE and GCC. You really want to do that for security reasons. The production images are all compiled, minus PIE, minus FPIC, and actually minus fortify source as well, as you'll see when we get there. But the story here is that these, the init function stuff works perfectly fine in that world. For the longest time, you were actually grubbing around in the ELF file looking for addresses of things put in magic segments. And that scheme, the moment the security guys told me, hey, dude, you better go do minus, minus FPIC, minus PIE. That scheme just doesn't work anymore, so we had to go disappear it. Moreover, this one works perfectly fine with the plugins, because as the plugins are sucked in, there we get. So back to main.c vnet. Oh, I guess we've only got one main. Oh. All right. I don't know why that didn't work the way I expected it to. At any rate, so let's go looking for a real honest-to-God main here. Here we are in main.c vnet, about line 136 for those of you following along on your laptops. And you'll see that this is kind of parsing is done in a particular way that's not done anywhere else in the executable, and you ask yourself, well, why is that? And that's because the stuff we're parsing here is go size the main heap, please. You want to get the main heap going as early as possible because plugins are going to expect it to be there. So what we do is yada yada yada, parse some arguments, get the memory subsystem going, or complain vociferously if it doesn't and give up. Then we set the getting the handoff structure callback. It turns out every plugin is going to want to find the sort of mother of thousands, the VNet main T, VLib main T, and Ethernet main T. In other words, the key data structures. Yes, we could put we could put set get, well, not set methods, but get methods in there, but truthfully, every plugin is going to want those three things. So we arrange to set it up and hand it to it when the plugins actually get going. We'll see more of that when the plugins, when we talk our way through actually building a real plugin. So out of here, we say, all right, well, that's real honest to God main and VNet main. So here we do VLib Unix main, which is the next place we go, and it's, again, over in VLib rather than in the container app. cscope. All right, I probably shouldn't have done it that way, but at any rate, here we go. So this is the next step in enlightenment, and you'll see we just about have set up the heap, and now we're off into doing plugin early init. Worth looking at plugin early init a bit. Okay, so over here in plugin early init, cutting to the chase, what kinds of things can you do? You can set, from the command line, you can say, well, where are the plugins that I want to load, without recompiling the thing. They default to a pretty obvious place, which is, in typical distros is user lib, vlib plugins, and user lib VP API test plugins, I think. And we'll have to go refresh my memory on that detail. But the right way of saying is all of that can be set from the command line if you like. Then load new plugins is basically an across all of the reasonable guys you find, and load one plugin is to go load a single plugin. DL open on the guy. It'll turn out that if you get back a null handle on something that's been discovered that has the right name, the likely thing is that there's an undefined symbol. And if you don't do something of this form, clib warning, mumble, DL error, nobody's ever going to know why the plugin didn't load. And again, ask me how I know that. The next thing we do is there's a VLib plugin register method that has to be in all plugins. It's the only canned name that the engine actually goes and looks for specifically. You do a DL sim to go find it. You say, get me the handoff structure. Well, okay, that's not really ever going to happen. Otherwise, you dive into the plugins init routine, which is to say you pass it VLib main, the handoff structure, and from early init, mumble one, mumble, some idea that we might eventually make it so that you can, load plugins later in life. There's a bunch of complexity to that. It's an implementation choice we haven't made at the moment. So at this point in the game, backing up into the main init sequence. Main.c. We're over here. Are we over here? Yeah, we're here. Whoop. Nope, we're not. Let's see, main.c Unix. Okay, so there's the plugin early init. We go use a function called unformat. We'll get to unformat in detail. Just think of it as scanfing through the command line arguments, setting a bunch of variables here and there. One thing to say about that scheme is it will eventually call all the configuration functions you have. The idea being load the set of plugins, go run all of the configuration functions. Configuration function in this case equals something to take apart the command line. You'll see how they're registered. They're real simple, but again, here's how you tell the DPDK I want so many threads in one thing and another. Vincent? Grab a mic.
Yeah, so can we load the plugin later on, or should it be only at the init stage? Can we load some of the plugins during the runtime of it?
At the moment, the only place it loads them is really first time. It can be done. I just haven't much wanted to.
But you don't see, for any reason, we could load it later on if
there's no reason you can't. The thing being, you're going to end up needing to go run back through. These guys will go. You'll have to go run the constructor lists and so on. There's no real reason you couldn't. It's just simply a matter of not implemented today. But yeah, perfectly valid feedback. If somebody wants to work on it, I'm not going to stop them, because again, it should be fairly simple sledding to make that work. Once you understand the thing, go for it. Grab a mic, please. Somebody, okay, red mic coming up.
I'm just curious, what's the threading model for the plugins then? Is it a single thread that's going to execute through that, or is it run to completion, or is that configurable? I mean, maybe I'm jumping ahead. Okay,
yeah, you are jumping ahead, but it's a good question. Might as well deal with it for a second. Plugins are just pieces of the graph. They can run in whatever thread happens to get there. All they're doing is contributing graph nodes. They can spin up their own threads if they like. When we get into how threads are spun up, again, it's going to be another one of those constructor macros. Make me a long list of them and then go bang through them. Guess what? We haven't gone through any of those linked lists yet, or we're just beginning to. The call all config functions guy does. Again, vlib plugin early init is so early that the only thing that's there is the heap, is the main heap. And oh, by the way, you can size it from the command line. So there's really nothing special about plugins except that they were built separately and thrown in a directory. So thread stacks. One of the things that we do is a little bit of trickery about making thread stacks. Even for, well, there are two kind of honest-to-God threads floating around in this environment: P threads and EAL threads. The EAL threads, are kind of as described. If you guys know about the DPDK some, the P threads are useful for things, for unbound runs occasionally kind of stuff. The stats scraper thread runs like that, where we don't necessarily need to give it a core. So. So there's, there are at least a couple. The third threading model are what are called in this code base processes, which are actually cooperating multitasking threads that run in the main EAL thread, which do things like, how would you put it? They're background processes that wake up every so often and send packets. That's the way the DHCP client state machine works, is that it'll have a process that wakes up every once in a while and says, "Hey, do I need any do I need to renew a DHCP lease?" Those are kind of cute little things, but not really germane here. So what we do here is we'll go and allocate nicely aligned stacks out of the main thread for each of the other kinds of threads we're doing. You'll notice, typical OS guy that I am, I actually, oh boy, that didn't get fixed. At any rate, that mprotect really ought to have a macro page size in it. Oh, I know why. Okay, I haven't pushed that change set yet. Blah blah blah. At any rate, we want to read protect the bottom page of the stack, so you get proper stack checking when and if one of the stacks ends up hitting the thing. You'll notice that they're fixed sized, allocated densely. Reason for doing that is actually straightforward, that the thread ID amounts to the stack pointer right shifted a ways. And we do that. You'll see in here a guy called OS get CPU number, which is, okay, which the heck thread am I? And that works by taking any old stack address and right shifting it enough so you get down to the, okay, which thread am I piece. Damian will talk more about that. CLib call jump is is a nasty piece of assembler code, architecture specific. What it's doing is it's saying, please go call this thing thread 0 on the thread stack that I just allocated. The idea being you want to get, this is the sort of fork exec internal guy. So at any rate, now that we've got there, let's go find thread 0. Well, he's not real complicated. What he really does is to dive into this guy vlib main. All right, now let's just go. Fine, global def. Right, and oh gosh, that was a real loser. Let's try this. How about, since I know where it is, main. All right. So here's the main function. Time init. This is a good topic. Internally, we use a floating point, a floating point number of seconds as a time base, and this guy, is setting up. It's a little complicated when you look at it, but what it's ending up doing is it's going to use the bus tick register, whatever it is, RDTSC instruction to go get the CPU clock, and scratch its head, do a little bit of arithmetic, and turn it into a floating point number of seconds, double number of seconds since we started. But those are used for things like scheduling, scheduling those cooperating multitasking threads that we'll get into in a minute. Mumble turning on the event log. I'm probably not even going to get into that today. Let's see. Register all static nodes. Let's do a little recursive descent into this one, which is to say what this guy is going to do is it's going to walk the linked list of all of those static node registrations so that the init functions can use them. It's basically going to set up the, the structures. X, find, gold F, and simple linked list walk. All of the walkers of those constructor function created single linked lists look exactly like that. I mean, they're just kind of about as simple as it goes. Register node, probably not worth a recursive descent, but at any rate, so you register all the nodes, a little bit of random buffer init, yada, yada, yada. Calling all the init functions. Now, remember I've yapped about this. Here's where we call the init functions. We set up the node graph. Now, the way the nodes actually work, as we'll see when we get into the dispatch functions, is each one has a computed vector of static and also dynamic next indices. This is the thing that builds the graph structure. In other words, when you say, I want to flush a particular packet down graph arc 3, this is the guy, vlib known main init is the guy that goes off and does that. Oh, gosh. All right. Well, that's an interesting one. Mike?
My leading question is just you're seeding it with the time. I was just wondering if it's used for anything security important.
No, it's not. It's not at all used for crypto stuff. It's used just for making random CRUD for the packet generator. Just making a random data pattern. It's not used for anything where cryptography is required. The only crypto stuff is in IPsec, and Damian will can give you detail about it offline. Okay, so call all init functions, get the graph going, creating the default buffer free list. Now, with respect to the DPDK integration, what we're really doing there is simplicity itself. The DPDK buffer allocator is the real buffer allocator. A lot of the stuff you see in the vlib vnet stuff is a bit historical in character, which is to say, back in the day, it had its own buffer allocator. And we've kind of catered to not redoing 300,000 lines of network stack. So what we end up doing is we say, okay, a buffer in this case, the canonical example is buffers come out of the NICs, they end up having headroom configured at compile time in the DPDK. We paint the VPP engine's buffer metadata right after the DPDK buffer metadata. We then use the remainder of headroom really as headroom for rewrite space for doing networking. And most of the graph nodes you'll see are really independent of the DPDK entirely. The DPDK driver, RX, and TX worlds know about it, but the rest of the graph is blissfully ignorant of it. So we've kind of layered that out, not even deliberately as an architectural decision, but rather as a, how would you put it? I wouldn't even say as a historical accident, but it's a historical reality that, again, I've been working on this stuff since 2002, and the DPDK wasn't in anybody's, list of things. This set jump and so on is just a bunch of tap dancing so we can exit more neatly. calling all the configuration functions. Now that the graph is set up, the buffers are set up, you can go, configure each of the subsystems. Calling all the main loop enter functions, of which there are not too many. This is to say, I want everything absolutely ready. I'm about to go dive in the main loop. Here you go. One last chance to do, to do some setup and configuration, and then vlib main loop. This is the guts. This is for the main thread. This is the guts of it. Oh, fine. And here we go. Whoop. And here we go. So, pending node vector. We don't want to worry about. I don't want to obsess about all of the details here. What I want to do is to say the cooperating multitasking processes are all fired up at this point. We'll walk through an example in detail. You fire up, and here finally is the while one loop. Let's go do stuff. When I was talking earlier about multiple node types, there are, as you'll see as we walk through this guy, which is the overarching thing that sits and runs around in the loop and makes stuff happen, you'll see that there are multiple types. Pre-input node is actually the, I wouldn't even say historical, it's the epoll dispatcher. We have buried in the infrastructure a way of watching, in parallel a set of file descriptors upon which you might get epoll pops. Examples being the debug CLI, examples being, file.io that you might have started. A lot of things in this world are very asynchronous, and what we typically do, there's a socket layer that'll do both binds and accepts, so that in the engine, if you want to set up a socket client that in fact does the same APIs that we normally do through shared memory, that can be done. It's a bit of a security hole. We don't have TLS in here. Ding, ding, ding. Somebody wants to add TLS. Ding, ding, ding. Might want to consider it. The point being. Those kinds of things, file.io-ish things, and also interrupts. In the near future, we're going to start using the DPDK interrupt scheme so that if on a real computer the vector engine is kind of snoozy asleep at 200,000 or 300,000 PPS, you don't end up sitting burning a core polling. If you wanted to scale to 1,000 containers, you have to get where you say, okay, well, not any one container is going to take a tremendous number of PPS. So the dispatch infrastructure, as we'll walk through it, you'll see it's kind of set up to do either interrupt mode or polling, and to swap between them when the vector size gets to a certain business. Again, as I said yesterday, the vector size below about 10 or so is just snoozy asleep. That you can interrupt the works for 10 milliseconds. You're not going to drop anything. You may get variable latency. For each individual packet. But again, in a container networking case, do you care so much? The answer is probably not. On the other hand, if you're doing hardcore networking, you want to be polling, and it'll break forward and back. The pre-input guy, again, rough summary is the input, the input poller. Again, debug CLI goes in through there. The input nodes are the meat and potatoes of, okay, we need a prime mover. We need to get vectors from someplace, and input nodes are exactly that. They don't, although they have the same function prototype as the interior graph nodes, which are handed vectors and into which vectors are pushed. Input nodes are those guys that make up vectors out of whole cloth. You'll see there's nothing magic about them, but that's what they do. The Q signal pending guy is an interesting detail. One of the things you say is, well, okay, we have API clients that have connected to us. How do they shoulder tap the main process? And what they do is they send it a signal. Signal handling, of course, is incredibly thread. You name it, it's unsafe. So what it does is it just simply sets a variable. And here's the nice safe place where you go scrape it and say, okay, let's go do the posted Q signal callback. If you wind your way through this particular trail of tiers, what you'll see is that SIG user 1 is set up to prod the thing and say, go look for an API message. Pretty simple story at the end of it. This is the top level in the middle of the while one loop detail, how that actually freaking works. Interrupts, as you remember, I said the things set up for interrupt as well as polling. Probably don't want to go too deep into that. It checks in the main loop is have any process nodes, again, cooperating multitasking threads, are scheduled off of a wheel timer, which is both highly efficient and cute. A lot of things that are inlined here could be done, more deeply. The thing being, we want this stuff to be as fast as possible. And my colleague Elliot Dresselhaus, who's the maniac clock cycle counter, chose to inline this stuff right here. Now, the meat and potatoes, the 97th percentile of all the graph processing is done in this loop right here, where you're saying pending frames. Now, what's a pending frame? Remember, we've been forming vectors of packets. Well, a pending frame is effectively a vector of packets plus, okay, what's the dispatch function I want to go shoot off? And you'll see that as we go into dispatch pending node, that's actually where the fun begins. So let's just take a quick look at dispatch pending node. And it's relatively simple. The last timestamp guy passed in is so that we can do fairly accurate statistics. Let's see, frames. Okay, a lot of this stuff you need to read through carefully offline. But what ends up happening is we goof around to take the frame that we're about to execute, get it out of the way. Noticing one of the things that won't be obvious here that I'll just tell you is that it's perfectly fine for a graph node to enqueue right back to himself as long as he doesn't do it forever, no problem. What this is doing is saying, okay, I'm processing a vector of packets using a particular dispatch function, and now what I'm going to do is get that out of the way, so if he wants to enqueue stuff back to himself, it's not going to make a chocolate mess or run the risk of overflowing or cause people's heads to explode in various ways. So that's what this whole dance about the allocation bit is doing. The tracing stuff is actually pretty carefully optimized. Ordinarily, why do you want the packet tracer? You want the packet tracer because the frickin' thing isn't passing traffic and you want to know why. When you see the packet tracer output, you'll get the idea, well, I want the code always there, always available, but not on. This is, again, an optimization scheme to say, oh yeah, I'm tracing some packets in this frame. Let me make it really obvious to the rest of the world to go do that in a way that doesn't burn too many clock cycles. And dispatch node, now we finally are getting warm and getting ready to go crank the function up. Find this symbol. Okay, dispatch node, if I can finally find it again. Right. And this guy's a bunch of, oh yeah, clibdebug. I should tell you all about clibdebug. When you build a debug image, and we'll talk about how to do that versus how to build a production image, the symbol clibdebug will be set to 1. You can actually set it higher than 1 if you want some fine granularity in just how much debug junk you're doing. The thing about a clibdebug equals 1 image is that the engine will run at least a factor of 10 slower built that way. That one of the things somebody was really paying attention yesterday to the demos noticed was that all of a sudden the ping round trip time went to shit. And the reason it did that was he was running a debug image. That truthfully the paint's just barely dry on the container image at this point in the game. So running debug images to get a feature to where it's solid is absolutely the way to go. And I'll tell you through some other tricks there. At any rate, mumble. Right. There's a little bit of speculatively prefetching the next nodes. As we get into actual dispatch functions, you're going to see that there's an awful lot of speculative execution being done, meaning you bank on the fact that packet I plus 1 goes through the graph the same way packet I did, and enough times in 10 you'll be right that it's worth going ahead and behaving as if that's always going to happen and then unwinding it after the fact. That when we get into the actual dispatch functions, you'll see that. Main loop event, that's strictly for debugging. Yeah. Yeah, there's a scheme for tracing the trajectory of any one packet through the graph so that if you're running into trouble, you can in fact in GDB, in the debug CLI say, okay, that packet right there, where did it go again? How did this possibly happen? Very seldom useful. VLib upper trace trajectory is a pound defined, so normally that stuff is compiled off. And now finally, oh my God, we went and called the node function. The bottom of this guy does some accounting and worries about switching between polling and interrupt mode. Again, turned off, disabled for the DPDK, but we will absolutely do it. This event logging stuff is a topic we probably won't get into. We have a scheme for logging events in the code path, which costs, I don't know what, maybe 30 nanoseconds or something to do a log entry. They're pretty printed long after the fact. Pretty printing of those guys is just a single call to printf is infinitely more expensive than processing a packet. So you don't do that. What you do is you scribble down some binary data and format it later if anybody actually gets around to caring about it. Yep. Mic, please. Grab the green mic there. Right there. Right there. Grab the green mic. Thank you. It's on.
Hello. Yeah. So you are talking about, I see a lot of the dispatching node, right? So node is actually some abstraction of the computing resource like the pthread, right? And
no, nodes in this case are actually either the node registration object or they're when it's which line are you talking about exactly?
I see a lot of the dispatching node, yeah, and also node function, right?
Oh,
so
okay. Node. This is it's a data structure. It's not a thread. It's a graph node.
It's graph node. Okay.
Yeah. Okay.
Okay. Thank you.
Yep. So, all right. So now we get down to go call the silly thing, and here's the magic that does some switching from polling to interrupt mode depending on the load. You kind of don't want to think too hard about that piece just at the moment. It's not even really turned on and used because effectively we don't have nodes in VLib node state interrupt at the moment. They're all just in node state polling. In fact, this whole stanza is shut off, but we're going to turn it back on as soon as we can because again, container networking, 1,000 instances, you definitely want to break, you want to use ePOL instead of just burning a core completely. So now, let's go back to walkthrough, get my brain back on. Okay, so we've gotten through a lot of this stuff, and right. Okay, do we want to take, take a 5-minute break and get people some coffee at this point in the game? So why don't we do that? The other thing is before we break, let's take questions from the floor. Is this all making sense to guys? Are you kind of getting it, or because this is the natural place before we start actually doing some demos. Other thing is if people's laptops aren't set up and ready to cook, you want to get that going right now. People good?
We need a VI parallel session.
Sorry. Yeah, well, yeah, I don't know. I apologize.
I feel like that's correct.
What?
You can just say where that file is.
Oh.
C-scoping and the VMs don't have C-scope set up.
Oh, okay. Well.
Or at least we haven't learned how to do that.
I'm Mike. Don't give. Oh, yeah. Yeah.
Well, it's.
Yeah, well, that's actually easy. In the Vagrant VM, if you've got it going, do sudo apt-get install cscope, and then just do a find from the VPP level of star.ch, and you'll get a pretty decent database yourselves. That's absolutely worth doing. Yeah, good point.
Is there a make command to build all the cscope?
Like I said, go find all the C and H files and run cscope minus d minus k minus I.
So it's not a make file.
No, it's not. Okay, so guys, let's what time is it now? It's 9:45. Let's reconvene at 10 and start doing some typing. Sound good, everybody?